Greetings. So in this lecture, we're going to talk about net change and future value. So here's kind of our setup. So we're going to suppose that we have that Q is a quantity changing. Okay, so we're going to suppose that Q is a quantity changing at a known rate Q prime. And let's actually kind of give that a different color, like orange. Okay, and so then we're going to have that. So we have two different kinds of definitions here that we should know. So the first one is going to be the net change in Q. And we'll box this because this is kind of the terminology. And we've used this terminology a little before, but I wanted to give you kind of this, and with it's going to be kind of two pieces here. In Q between, and then you're gonna kind of recognize that these are bound. So this is between T equals A and T equals B. Okay, and what this is going to be is, so this is going to look to you like the integral, as it should. So we're going to take the Q values at these bounds and subtract them. Just like that. So that should look like the integral to you. And in fact it is. So this is the integral of, and then we go from T equals A to T equals B. And then, right, we want to take the rate of change inside the integral. Okay, so that's the first thing. So this is our net change. There's also the future value. Okay, of Q at a future time and let's make this, I'm going to use this red again, of course, because we always have limited colors. So this is T greater than 0. And what this is going to be, so I'm going to take the difference here. So I have Q of T here. Okay, what this is going to equal is it's going to be, I want to apply Q to 0. So like having at time 0, I want to get rid of whatever was happening at time 0. Plus, and then I want to take the integral from 0 to T of this Q prime of X. Q prime of, now I want to write, I'm actually going to write this as x dx because we've kind of fixed a time. So I don't want it to be my dummy variable anymore. Okay, but otherwise you can tell that these kind of look the same. I've just said at a particular time t. Then I'm looking at, I want to know what this future value is. And so I take, if I move this over to the other side, this would look exactly like that. Except that I kind of changed because this would be like my b and this would be like my a. So I had to change the dummy variable because my b is called t. But that's the only difference. Otherwise, this is exactly like from before. So let's do an example. Okay, so example 1. Seeing how far to the left I can write and still stay on your board. Okay, so we're going to suppose okay, so there are going to be 100 COVID cases at time t equals 0. Actually, I have this fully written out nicely in the notes, but I don't think I want to write out all words on the board. Okay, so there are 100 COVID cases. At time t equals 0. And, okay, the number of cases, which we're going to denote by NT, okay, increases at a rate of n prime of t equals 90 e to the minus 0.3 t cases per day. And then what we're tasked with is going to be NT for t greater than or equal to 0 days. So N of t for t greater than or equal to 0 days. Okay? So now let's kind of continue on to actually do this. And we want to coordinate what's going on here. So we're looking at a future value problem. Okay? So this is going to be, so the plan, this is a future value with so we're going to use that equation up there. Okay, so my Q is going to equal, so my Q of 0, I have this here. This is the same thing as like my Q of 0. I'm not sure what color to use for that. So my N of t is like, this is like my Q of t. Okay. This would be like my Q prime. Okay. And this is like my Q of 0. And I'm just going to, this is my Q of 0. Actually, it's like this one exactly. So let's put the arrow there. Okay. And then t is my t. Okay. So otherwise we can just kind of use this equation. So there we go. So we're going to get, so here's my solution. Okay, I want to have, so I have N of t. So I'm just using this formula here. So this is the formula we're going to use. So I'm going to put a star next to it. Okay, so we're going to use star with N of t replacing Q of t. And the other kind of substitutions that we talked about over there. Okay, so we're going to get, so my solution is going to be N of t is going to equal, so we have N of 0 plus, and then we have the integral from 0 to t. And then this is where we need this N prime of t, or N prime of x, right? We want this to be our N prime of x dx. And then we'll go ahead and make, so this is just like this t here. This is actually kind of the t that we actually want. So let's just make this, there's just going to be the t that's going to go there and going to go there. Okay, and then, and we have bounds on this. We have, so we have everything we need on there, except what we're going to put in. Okay, so we have two things to worry about, N of 0 and N prime of x. And from over here, so we're going to use this with, and this is where we take what we have from over there. So we have that our N prime of t is going to equal 90 e to the minus 0.3 t. And then the other thing that we need is our N of 0. And this comes from here. This is this 100. Okay. Let's move this up a little bit. So this is with, so these are the things that go into that equation, and we go ahead and do that. Okay, so we get N of t is going to equal, and then we have this n, and maybe I'll still make this red. This is kind of important for us. Okay, so we're going to have this n of 0 is 100 plus the integral from 0 to t of, and then we can replace in for n prime of x, this equation we have here. So we have 90 e to the, and because we want it to be of x instead of t, we want to put that in as an x. So it's kind of an important detail there because we want to look at a specific t at this time. Okay, this is a substitution problem. So this is also more exponential practice. This is actually a substitution problem here. Okay, where my u is going to be the inside function, like always, so it's right there. Okay, so we're going to use u equals minus 0.3x. So my du equals, remember we take the derivative of this, so that's going to be minus 0.3, and then we have dx. Okay, and then we usually like to do this thing, so we're going to move this to the other side. Keep in mind, this is actually 3/10, so I could actually do this as minus, and then if I wanted to bring it to the other side, right, so not to reuse colors here, but this is actually 3/10, so to bring it to the other side, I flip that over and I get 10/3. Okay, so I get minus 10/3 du equals dx. Okay, so now I can substitute that in here. So I go ahead and do that, and I go get that n of t is going to equal 100 plus, and then remember I have to change my bounds. Okay, so this has to be u of 0, this has to be u of t. I was just like, U of T, like University of Toronto. That was why I laughed. It's not that funny, but, you know. Okay, 90 e to the u, and I replace dx here with my minus 10/3 du. So now that this is all in terms of u, okay, so I'm going to get n of t is going to equal 100 plus, so u of 0, so I'm putting 0 into there. So I'm going to get out for this, I get out 0 actually, because I just substituted it into u here. The same thing for t, except that I get minus 0.3t. Okay, substituting that in. And then I can pull out actually, I've got what, minus 900/3, so minus 300. And I didn't pull that out yet here. Let's just kind of scoot this all over to make room for that. Okay, so I've got my minus 300 here in front of this integral, and I still have that 100 there, and this equals n of t. Okay, and now, so now that I've done that, I just have e to the u du. Okay, so now I can go ahead and actually compute this. I know that it feels a little weird because there's a t here, but we're kind of fixing that. It doesn't matter. It doesn't it doesn't have a relationship to u, so it's okay. We can just go ahead and integrate this. So this is going to equal 100 minus 300, and then big parentheses. So I put my parentheses here. I'm going to want to put in something slightly big, so I kind of make that big. Can't actually, oh, that one doesn't need to be that big actually. Okay, so I'm putting this in on top. I'm actually getting my glasses repaired, which is why I'm not currently wearing glasses, which is why it's harder for me to see things sometimes here. So I apologize for that. Okay, and we notice here, before we do anything else, so e to the 0 is 1, so that makes our life easier there. And we have, so we can go ahead and do this. So I'm going to get that this is going to equal 100 minus 300 e to the minus 0.3t, and then, you know, I have a minus, and a 300 here, and a 1, so this is just the plus 300. So in the end, I'm going to get, so I have 100 plus 300, so that's just going to be 400, and then with this, so I have n of t is going to equal 400 minus 300e to the minus 0.3t. And we're done. And we don't need a c because it's had bounds, and we never had to go back to x because we had bounds. Okay, great. So this is just one of these examples. As long as you know kind of, it's like you have an initial value like this, and you're looking for, you know, we've seen things very similar to this before, but I've kind of put this into a context of, you know, I put this into kind of a formal context for the future value. And we're just able to do this here, so n is our function, we have its derivative, so that kind of replaced our q prime. We have what happens at time 0, so we can replace that there. We have this, we're looking for n of t at t, so this is good that this is here. And then the difference between these, keep in mind, is that this t here now becomes this fixed, almost like a constant there, and so we need our dummy variable to be x. So that is a change that's done on purpose. And then this is just going to end up, so I just took this equation from here, and I just put in all of my stuff to change it to be in terms of n, and then I just, this was the stuff that I got from the statement. Okay, so then I got to here, and this was a u substitution. We've done u substitutions quite a few times now, so hopefully that's fairly straightforward. And the other thing being, so it's okay to put t, like treat it like a constant when we put it into there, so I get minus 0.3t. 0, when I put it in there, gives me 0. So those are my new bounds. Now everything's in terms of u, so I can just compute it straight out like I normally would, and I actually am able to get my function like that, where now t is the variable, but when we computed for it, we treated it like a constant. So that's like a really important point of what's going on here. Okay, great. So I hope that made some sense, and it's also starting, hopefully some of the stuff is starting to solidify as we're using it more and more. And I will see you in the next lecture.